My name is Diana Burk, and I'm a postdoc in Dr. Bruno Averbeck's lab. I'm going to talk today about a project regarding impulsivity in decision-making. In particular, how impulsive choice strategies can maximize rewards in unstable decision-making environments. Impulsivity typically has a negative definition. Take this classic one, which defines impulsive actions as actions that are poorly conceived, prematurely expressed, unduly risky, or inappropriate to the situation, and often result in undesirable outcomes. However, in reinforcement learning, there is often a trade-off in most decisions to take an immediate reward or a future potentially larger reward. We can formalize this by considering a graph of a state space for a decision-making process with nodes representing choice points and edges representing transitions between states. In this example, there's an immediate possible outcome and 6 possible delayed outcomes that require multiple choices. An agent could choose the immediate reward or try to get to the 2 desirable outcomes shown in green. The question is, how much can the agent control its path through the state space? This might be challenging depending on the transition probabilities. What if the agent selects a series of actions that leads to the node in purple, and then the transition probabilities favor the positive outcomes? Then it obviously is better to take the future option. However, what if the future positive reward is very uncertain or equally likely to be negative or positive? Then the question becomes, should you take the immediate reward? And can impulsive agents potentially perform better than patient agents in particular decision-making environments? We can model some decisions in reinforcement learning as Markov decision processes. In this model, an agent considers all available actions at each time step in a particular state and selects an action to maximize reward over the entire episode. The utility of a state S at time t is defined by this equation and is maximizing overall action values in that state. Each action value is a function of the immediate reward, cost, and potentially future possible rewards that can also be discounted. This is where the trade-off between immediate and future rewards comes in. The term in the summation is the transition probability to a particular state if one takes action A, and gamma is a discount factor that defines the extent of discounting for future rewards. So the model seeks the most valuable actions to maximize this overall reward. And we use this to model 3 different decision-making tasks. In the first task, I'll go through a little more detail, and the other 2, I'll just mention the results. The first task is a temporal discounting task, which asks whether an agent wants a small reward now or a future larger reward. If we take a look at the state space, we can represent the 2 actions or choices using 2 states for the immediate and delayed reward state, and each time point with a continue state or an exit non-rewarded state when thinking about the future reward. And we can manipulate the transition probability to reflect the volatility of that future reward. In a simple example, in a high certainty environment, there would be little chance of losing that larger reward along the way, and the expected value would be higher. So the best action is to take that future reward. However, in a low certainty environment, where it's highly likely that the future reward will never come, the best action is actually to take the immediate reward. Recall the main action value equation in the discount factor. If the transition probability is very low, that means the possibility of no reward is very high. And if the discount factor is very high, then the future reward will be taken more often. So in a certain environment, this fares very well for the agent that has the higher discount factor. We can see on this bar graph on the right, over many trials, the average reward is higher for the agent with the larger discount factor. However, if the environment is uncertain, then the agent fares better by actually taking immediate rewards. So the impulsive agent actually does better than the agent that has the larger discount factor. We extended this idea to 2 more decision-making tasks, information sampling and novelty. In the information sampling or beads task, an agent has to guess what the majority color is in an urn of beads, but they get 1 bead at a time and accumulate draws before making a guess. Each bead has a cost, so too many draws and the cost is higher than the reward for even guessing correctly. We manipulated some of the task variables to create certain and uncertain environments, including the fraction of the majority color and the cost of guessing correctly. When the environment is certain, the fraction of beads in the majority urn is high, and the model can rely on that information so that an agent with the higher discount factor gets more average reward and guesses correctly for drawing more. However, if the environment is very uncertain, where the fraction of beads is low and the cost of an incorrect guess is high, then the overall cost grows with excessive drawing, and the higher discount factor actually does worse than the impulsive agent. In the novelty task, an agent has to actually explore multiple options and learn the value of the rewards. And in this task, every once in a while, a novel image is substituted for a known image, and that value needs to be explored in order to know what its value is. In a certain environment, when the substitution rate is low, then the agent with the higher discount factor does better exploring all the options. In an uncertain environment, when the substitution rate is very high, the agent with the lower discount factor actually does better by sticking to options that are better known, and rather than exploring the novel options that will soon disappear, and overall accrues more reward than the agent with the larger discount factor. So in summary, we have shown that we can model different types of decision-making behavior using the discount factor and MDP model. When the agent's discount factor is appropriately matched to the decision-making environment, they do receive the most reward available. And this might seem obvious, but we're showing that impulsivity might not inherently be negative, and impulsive agents can fare better when making a decision in an environment that has uncertainty. And this is a framework that could help us understand impulsive human behavior as an adaptation to different environments rather than inherently a negative affliction. And with that, I would like to thank everyone in the Averbeck lab, the LN staff, and collaborators. And if you have any questions, please feel free to email me or to reach out on Discord. Thank you for listening.